Hi, this is Professor Dorr, and this is Lecture 11 of EE 310. And the title of this lecture is Effective or RMS Values. Now, of course, in this lecture, you're going to see the magic relationship of square root of 2 or 1 over 0.707 that relates peak and RMS values. And you'll see that that's for sine waves. But we're going to start from the basics in this lecture, and we're going to show how to get the RMS value of any periodic waveform. And from there, what you'll see is the 0.707 and the 1 over root 2 relates to the special case of when we're working with sinusoidal values. So any waveform has an RMS value, but for sine waves, that's where those constants come in. So of course, we're going to do a bunch of problems, and I'm going to give you some practical stuff that will give you insights and hopefully help you with your job interviews, so you'll all go get wonderful jobs. So all the stuff I just mentioned actually starts on page 5 of the lecture. Before we get started, I want to start off by reviewing maximum power transfer for AC circuits from our last lecture. So let's get started. So I put this statement here all by itself because this is a really important statement. One of the few things that I can actually remember. And what it is it says for maximum average power transfer, the load impedance, Z sub L, must be equal to the complex conjugate of the Thevenin impedance. And this is maximum power transfer properly stated. You might remember in the last lecture, I gave you a little banana peel tricky interview question where I said, given this load, tell me what the source impedance should be for maximum power transfer. And of course, it turns out that the source impedance should be 0 for that case, because I didn't state the problem correctly. So the way I like to think of maximum power transfer is you are given a source. You're given a Thevenin source, and you got to find the load that will get maximum power out of that source. Let's do some practical stuff because I want to give you a sense of why this matters. Why is this so important? So I drew a little picture here. I really wish I could draw because I like simple little drawings like this. This is not from Star Wars. It's not one of those things that Luke Skywalker drives. This is my lousy picture of a satellite. And so this is the satellite that is driving the little direct TV dish on your house. So this is a satellite antenna. I didn't draw it that way. I drew it more as a mobile radio antenna, but yeah, that's just a detail. So the signal from the satellite comes down and it hits this antenna. And from the antenna, we have a piece of coaxial cable that goes into our radio receiver. The radio receiver does a whole bunch of really cool stuff. After working with radio receivers for 35 years, I think the stuff inside is even cooler than I thought it might be when I was learning. But eventually it ends up as coming out as an audio signal or a text or something like that. So we got a satellite, and it's sending a weak little signal down to antenna. Antenna picks it up, puts it in a wire, goes into the radio, and eventually it gets to something that tweaks one of our 5 senses. We're engineers. Let's draw a simplifying picture. So I've got my satellite and I've got my antenna. Antennas are complicated. If you're really smart and you're really good with Maxwell's equation and multidimensional calculus, go design antennas if it looks like it's something fun, because not very many people can do it. And I'm one of those who can't do it. So what I do is I say, okay, satellite an antenna, what you look like is a Thevenin source. So you can see I drew my little dotted line. It's kind of hard to see, but it starts here and it goes right through that cable, and then I show it right here. That satellite transmitter, the ether that it goes through, the geometrical shape of that antenna, etc. At the end of the day, it's just a Thevenin source. Now, that satellite may be putting out 200 watts, and that power, by the time it gets back down to the Earth, is spread over a massive, massive area. So this little antenna is going to pick up just a tiny, tiny little bit of power, like picowatts we're talking about. So when that power gets into my radio, and you can see here I've delineated the satellite and antenna, the radio, and then the user. When that signal power gets into the antenna, there's Brownian motion, there's thermal motion in the resistors, in the amplifiers, etc. And just the thermal noise in my receiver can be as big or bigger than the signal that I'm getting from that satellite. So what do I want to do? Duh. I want to get the absolute maximum power that I can out of this source. And so therefore, what do I do in my radio? I make sure that that antenna sees a complex conjugate load. In RF speak, and remember this because it's good for your interviews, is we have matched the load to the source. So my Thevenin impedance here was the Z Thevenin, and I put a load on it of Z Thevenin complex conjugate. So now I have the absolute maximum power that I can get out of that little antenna. If I want more power, I got to make a bigger antenna. That's going to be more wind loading. It means when the wind blows, it's going to rip the eaves off your house. So you don't want that. You want the smallest antenna you can. And so we've got the maximum power we can, and we want it to be greater than that received noise power by some amount so we can get some useful signal, not just gibberish out of here. So this is just one practical example of maximum power transfer. You're going to see a lot more in this class. I'm actually going to do a problem where we're going to talk about the car wash that, they have car washes at gas stations now. I don't use them because I drive really old cars and they trash my cars, but you probably don't use them because you guys don't have the money. But some people do, and you're going to see a maximum power transfer, a few lectures down the line. So I guess my point is, as a concept, maximum power transfer, load matching, impedance matching, power factor correction is all the exact same stuff that we did in our last lecture. One final cool thing for your job interviews is antennas are typically designed so they present a 50 ohm Thevenin impedance. So typically you can treat your antenna as a resistive Thevenin source at the band where you're using it. That's just a nice little piece of information to have. Okay, so let's say that your Thevenin source is complex, or in other words, it's R plus J something, or it's R minus J something. Well, if it's plus J something, then it means that you've got an inductor here, and of course you're going to want a capacitor here because that's going to be minus J something. But what if you say, I don't feel like putting a capacitor here or an inductor here because it just increases the cost of my radio receiver. I'm just going to put a resistor there. It's not going to be perfect maximum power transfer, but how good is it going to be? So here is an equation that's given in your book, and they have a really nice little derivation that's not just nice because it's a nice derivation, but it's a good example of how the Siegel would say, okay, what's the best resistive load I can put on this thing? And so it turns out that the best resistive load, the one that will give you the maximum power, is going to be the magnitude of Z Thevenin, or in other words, square root of R squared plus X Thevenin squared. That's the best you can do with just a resistor. And I'm going to do an example for you down the line here a little bit, where you're going to see that sometimes it really doesn't make a lot of difference, and you don't lose a lot of power, but you do save money on your design because you didn't put that component in there. Remember, when you're making stuff and you want to sell a lot of them, you don't want to leave anything on the table, because otherwise your competitor will, and then people buy your competitor's stuff instead of yours, and you won't make as much money. Okay, so let's do a little problem here where I want to find Z sub L, or the load impedance, that's over here, for maximum power transfer from this source. So my dotted line is going to go from here down, because I'm going to call this thing a Thevenin source. So I'm going to find Z sub L for maximum power transfer, and then I'm going to find R sub L for maximum power transfer. Or in other words, I'm going to use this right here afterwards. And then I want to find the load power in both cases, because I really want to see the difference between that perfectly matched load and just the resistor. So with a lot of these problems, they all come back to just making a Thevenin source, because in our strategy, we know that once we represent this thing as a Thevenin source, it's easy to get the load for maximum power. It's just Z sub L equals Z Thevenin conjugate. Or if we can use a resistor only, like in this part of the problem here, all we need to do is get the magnitude of Z Thevenin. And so really what this problem is about, 90% of the work on this problem is just getting your Thevenin equivalent. And so our power, we're going to use the little formula that we developed at the end of last lecture. And I tend to not remember this formula because it's really easy to just derive it from first principles, and it only takes me 20 seconds or so to do, but we'll use it because it's a good little formula. It's in the book. And then this is our power when we have a matched load, or we have a perfect conjugate load. The power when we only have a resistor, what I'm going to do is I'm going to just solve for the current and then say power is equal to I squared R. So that's my strategy. So if you're not good on the strategy, stop the video and go back and make sure that that strategy makes sense to you. Because if I saw this problem on an exam, I would, first of all, just like the seagull, I would go, ugh. But then I would go, hey, wait a minute, make a Thevenin source, blah, 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 blah. And I go, I can do each one of these. And the good thing is then my stress level goes down and then I can think straight. So I want to get the Thevenin impedance of my Thevenin source. And remember, my dotted line is here. So my Thevenin source is everything to the left. So we want to make a Thevenin equivalent. So that means we disable our current source. So that means it's effectively out of the circuit, right? And so what do I see looking in? I see 5 ohms in parallel with this clump of stuff. I see 5 ohms in parallel with this plus this plus this. And J10 minus J4 is going to be J6. So remember, current source isn't here. So really, I have 5 ohms in parallel with J6 plus 8. So let's do that. So Z Thevenin is going to be R2 in parallel with 8 minus J4 plus J10, or R2 in parallel with 8 plus J6, and now I'll put the numbers in, 5 ohms in parallel with 8 plus J6. So now I use my formula for combining parallel impedances, and it's really the same formula we use for parallel resistors, so you know it already. It's just that we're using complex quantities instead of resistance, and we stick that into our calculator or MATLAB or whatever we have, and out pops our Thevenin impedance. And remember, that is what I see looking in here with all the current voltage sources disabled. Now let's get the Thevenin voltage. And how are we going to do that? Well, of course, we don't have a load here because we really want to just measure the voltage of our Thevenin source. And since there's no load, the voltage at the output of the Thevenin source is going to be the same as V Thevenin. So that's why I say I can get my Thevenin voltage just by looking at the voltage here with no load. So what am I going to do? Let's see. I see a current source here. Doesn't look like I can move the current source somewhere to make it easier to work with, because you can see it's kind of in the center here. If I moved it, I'd just make a mess. So I see a little fountain. See the current squirting up in the fountain, and it's going both directions. So I got some current going this way, and I got some current going this way. So how could we get the voltage right here? Well, we obviously need to get the current in this path, right? Because if I can get the current here, I know the voltage across the resistor. So as I'm thinking strategy, I'm saying, okay, I want the voltage here, but what I'm really looking for right now is the current right here. One way to do it is to take these two and put them in parallel with these two. And that's going to give me just one impedance. And then I'll jam my current source through that impedance, and that'll get me the voltage here. And then I will do a voltage divider of the 5 ohms and the J10. Perfectly good way to do this. Again, I'm going to put these two in parallel with these two. That gives me just one impedance, one clump. And I'm going to shove 12 amps through there, and that's going to give me the voltage here. Then I'm going to do a voltage divider right here. Now, I'm going to be perfectly honest with you, and in industry, that is exactly how I'd solve this problem, because something in my brain just doesn't remember the current division theorem. But that's the way you really want to do it, right? So the current division theorem is always weird because it is equal to the current times the current in the right branch times this. I'm sorry, let me stop. What's the current division theorem? And now you can see why it bothers me, because what it is I take my current, I multiply it by the other side, right? I want the current here, but I'm going to multiply it by the other side and then divide it by the sum of these. And that just messes me up. But here's the formula. So all this stuff right here is the current in the right branch, and I multiply it by 5 ohms, and I get 23.41 minus J 29.27. This is the way you should do it. It's not the way I do it. I would do it with a few more steps so that I could just go from first principles. But bottom line is, when we're done, we have the Thevenin representation for this problem. Or in other words, to the left of the line that I'm drawing here, I can represent everything over here by this. Now, people have asked me, and this is a good question for rookies. They say, well, when you get the Thevenin equivalent here, is this current right here equal to this current? I mean, when you got your Thevenin equivalent, what's the current here? And I say, I have no idea, because my Thevenin equivalent only covered this dotted line here. So it only covers just right to the left of my dotted line. But how I got to that Thevenin equivalent, I could have got there lots of ways. So there's no unique relationship between my Thevenin equivalent and this current here or this current here. I lost all that when I made a Thevenin equivalent. But remember, my goal was just to represent everything to the left of the dotted line with a Thevenin. And here it is. So, like I said before, the problem, most of the work in this problem is just getting your Thevenin equivalent. Because once I have that, I can say, here's my Thevenin equivalent impedance. Here is my complex conjugate of that impedance. And you see my plus 0.732 went to minus 0.732. So there's your Thevenin impedance. We're going to use our handy-dandy formula for the maximum power. And we're going to say that we get 51.42 watts, in our matched load. And our matched load, of course, I see a plus here, so that's got to look like an inductor. So our matched load is going to look like a capacitor in series with a resistor. And I'm going to get 51.4 watts in that capacitor. In that resistor. So now let's find for the maximum power in just a resistive load. So we're going to ditch the capacitor and we're just going to use 3.49 ohms here, right? And the 3.49 ohms, of course, is the magnitude of this impedance. So we're going to put 3.49 ohms here. And now I want to know how much power I'm going to get in that 3.49 ohms. And we don't have a handy-dandy formula for that. So I'm just going to go back to first principles. And what I'm going to say is, here's my circuit. Here's my Thevenin impedance. Here's my resistive load. I can get the current, and then I can go 1/2 I max squared R to give me the power here. So my current is going to be my voltage, my Thevenin voltage, divided by all this stuff in series, and here it is. So now I'm going to say power is equal to 1/2 absolute value of I squared times R. Remember how in the last lecture I said this is how most engineers remember it, so they don't have to deal with that phase angle. If you're not sure about that, go back to that lecture because it's a really good trick. I mean, the basic idea is if I want the power through the resistor, all I need to know is the magnitude of the current in the resistor. So I don't have to worry about the exact phase of that current because average power doesn't rely on phase. So go back to that piece in the last lecture if you didn't get that, because this can save you a lot of time on exams. So the power is 1/2 times the magnitude of the current, 5.4 squared, times 3.49 is 50.88 watts. So with a resistor by itself, I got 50.88 watts. If I added that capacitor, I got 51.42 watts. Now, if I'm making a bazillion receivers because I'm making cable TV boxes, as a designer, I'm going to feel like a monkey if I put an extra component in to just get this small additional amount of power. So that's why if you're doing a problem like this, just take a look and say, is this thing even worth matching? In this case, it wasn't. So just practical stuff for you to remember. Okay, now let's get to the part of the lecture that I gave you the advertisement for in the beginning. So now we're going to talk about RMS power. And from equation 1111, or from our little derivations in the last lecture, we have the power in the resistor is equal to 1/2 Vmax times Imax. And that 1/2 is just going to get a little bit messy on us. So let's say that instead of kind of giving it a quick numeric fix, because you know for sine waves we're going to put in a √2 in there, but I don't want you to do that yet. What let's do is let's introduce a new concept. And the concept is more important than the √2, I would say. And it's really a simple concept once you get it. And like so many things, our textbook, Alexander and Seidecu's Electric Circuits, just said it beautifully. So I just lay out what they said right here. The effective value of a periodic current is the DC current that delivers the same average power to a resistor as the periodic current. Now that's a beautiful description, but I think it's beautiful to me because I already know it. But it's really concise, and as engineers we like to describe things nice and concisely because we want to add those up to make complicated things. So like so many things, the picture really helps me. So here we go. Here's a periodic current. And so I drew a little arrow here and I said, this is AC. And that's why I say it's I sub t, in contrast to over here where I just have a DC one. But so here is my AC periodic current. And it's going into a resistor. And so here is a DC source. It's a DC current source, and it's also going into the exact same resistance. And when I look at these resistors, they have the same average power. I want you to put a little caret right here and write average power. So in this resistor's case, it's going up and down and up and down and up and down. In this resistor, the power, instantaneous power in this resistor is going up and down and up and down. In this case, I have DC, and the instantaneous power is just sitting there, right? So, but if I average this power, I'm going to get the exact same average power as this resistor. Let's make our resistors into light bulbs. Do I still have my light bulb? Sure do. So let's say that our resistor is our light bulb, and I'm going to put my hand over the one on the left, and then I'm going to put my hand on the one on the right, and I'm going to go, they're both just as hot. Or I guess I could say the light is just as bright, but this one is actually being driven with AC. So the effective value of a periodic current, this periodic current, is the DC current, this current that delivers the same average power to a resistor as the periodic current. And that is what we call the effective value. So as you're working these problems, as you're studying for the quizzes, as you're thinking about this, don't get hung up in your √2. Don't get hung up in the integrations that we're going to do. Make sure you're cool on this concept. Because if you're not cool on this concept, everything else that you learn in this lecture, when you're done with this class, you're going to go, and you're going to flush it all down. And I don't want you to do that. If you remember this, the integrals and all the other stuff we're about to do, is something you can always rederive or come back to. But this will give you the insight you need to know what you need to do. So I like this little graphic. This really helps me. Let's jump into the math. So I'm going to take my statement here and I'm going to convert it to math speak. The average power, remember the same average power, is going to be for my AC circuit, it's going to be 1 over the period. Remember, we're talking periodic signals here, right? 1 over the period times the integral of 0 to t of I squared times r. Or in other words, we are taking our instantaneous power and we're integrating that, and that's going to give us an energy, right? Because I'm integrating, and you're going to see a little graphic of that in a bit, but the result of this integral is an energy value. We're going to divide that by time and we're going to get power. So that's the average power for my AC source. What's the average power for my DC source? It's I squared effective times R. Duh, you already knew that. So what I've done is I've taken the statement from whatever the half of your brain is that does words to the mathematical side with this little relationship. Okay, so let's kind of take a look at this in a little bit more detail. This kind of looks like the Golden Gate Bridge, but it's not the Golden Gate Bridge. What I'm looking at is the instantaneous power of that resistor when it's driven by some source. In reality, if we're really just driving a resistor with an AC source, then we would end up coming down to 0 in the middle, wouldn't we? Because when that AC source goes through 0, I got no instantaneous power. But I kept it general. So this is, we're plotting with respect to time, and this is I squared t times R. It's the instantaneous power. The integral, remember this integral right here is this integral right here, and it is the area under here. It's the area under here. If we were actually in my class and I was in front of all you, which I sure wish I was, I'd tell you the story about riding bikes across the Golden Gate Bridge with my daughter and spitting off the edge, and the wind actually picked up the spit and brought it up, and it went blop right on the car's windshield. And we thought that was so funny. We did it a few times, but it was amazing what the wind did on that bridge. But I'm not going to tell you that story because we're online and I got to behave myself. So this area is the integral. And this is the energy per cycle. Because what am I really doing? For my energy, I am the integral, I'm multiplying energy by time. That gives, power, I'm multiplying power by time in the integral. That gives me energy. So that means this area is the energy per cycle. So now what I'm going to do is I'm going to take this area and I'm going to give it a squoosh and I'm going to make it rectangular. And then I'm going to get this value right here when I divide by t. Or in other words, I'm dividing that area by t, so of course I'm going to get this, and that is going to be my average power. And so now let's relate AC and DC. So my I squared effective times R, which is I got from the DC, now we're going to substitute in our average power from the AC, And I'm going to take that r and I'm going to put over here. So I'm r over t times integral 0 to t I squared dt. I'm just doing what I said I was going to do. I'm relating the dc, which is on the left down here, and the ac, which is on the right. And here they are. So now let's solve this for I effective. And what do I see? I just kind of put my, looks like my r's cancel out. And I'm going to take my square root. And here is my formula for the effective current. Is this formula associated with a sine wave? No. This is completely general because we said, hey, you can give me any waveform you want here as long as I can get the area, and then I do my little flatteny thing, and then I pull off my average power. This is not specific to a sine wave. Let's look at something else cool about it. Is it specific to the circuit or the resistor? The resistor canceled out, didn't it? The resistor canceled out. We did I squared effective times R, and it is gone. So we don't have the resistance in our formula here. So what the point I want to make on that is that the effective value of a voltage or a current, it is only associated with that voltage or current. It's not associated with the circuit. So when I talk about I effective, or in a minute IRMS, I'm not talking about the circuit. I'm just talking about that source with the little, the little circle with the current arrow or the voltage, the plus minus terminals. So I effective or IRMS describes that current or voltage only. It has nothing to do with the circuit. So now we've got this effective value, and that's kind of what we talked about up here. We said the effective value. But now let's look at that effective value a little more. It is equal to the square root, that's the R, of, hey, I squared t integral divided by t, that's the mean square. That's the average square of this waveform. So what let's do is let's call I effective the root of the mean square, or RMS. And that's what we're going to be calling it. So RMS, we use it so much, sometimes we even forget to capitalize it. Let's do a problem now. So this problem, we want to find the RMS value of this triangle wave current source. And then if that current flows through a 9 ohm resistor, we want to calculate the average power. I like the way they divided this problem up because they said, first of all, find the RMS value of the current. Remember, the RMS value, or the effective value of the current, relates only to that current. So they said, tell me about the current first. Then let's put that current through a 9 ohm resistor and give me the average power. So I like the way they did that. So what we're going to do is use our formula for I effective or RMS. I often call it I effective, even though in industry they don't really use that term, because I just like to remind myself of what it is, and I always think of the AC source and the DC source. So using our equation, which remember is, I effective RMS, root of the mean square. See that? Root of the mean square. So I'm going to go ahead and just compute this integral. So the slope of the line is 16 amps per second. And so I of t, at least from 0 to 1, is going to be 16 times t for 0 less than t less than 1. Oops, I forgot to do something before I got started. And that is, I forgot to note the period of the waveform. The period of the waveform is just how long it goes before it repeats. And in this case, the period is going to be 2 seconds, right? Because after I've got to 2 here, I do the same thing I did back here. So it's a 2-second period. But from time 0 to 1, 0 less than t less than 1, it's 16t. And I squared is equal to 256t squared. So if I evaluate, or by inspection, I can say that the integral from 1 to 2 is going to equal the integral from 0 to 1. So I could do my integration all the way across here. And remember, I'm integrating the square of it, so it's actually going to go bzzz and then down like that, right? It's going to go up and down. But what I know is that from 1 to 2, that area is going to be exactly the same as from 0 to 1. So I can simplify the problem by inspection. So here's my statement. The integral from 1 to 2 is equal to the integral from 0 to 1. So my I effective is going to be 1 over t, that's 1 over 2, multiplied by 2 times this integral. See how I put that 2 here? I said double the integral and integrate from 0 to 1 instead of from 0 to 2. Just keeps it simple. If I wanted, I could have determined the equation for this line and integrate it, and I get the exact same answer, but I use the symmetry to simplify it. So here is my integral that I want to solve, and I get my 256, and the t squared integrates to t cubed over 3, and I put my limits here, and I shove all that in there, and I get 9.23 amps. What does that mean? What that means is that I have my AC source right here, and it's doing its little triangle wave thing here, and we're going to put that current into this 9 ohm resistor, and we're going to get the exact same power in the 9 ohm resistor as if we had a 9.23 amp DC source. Equivalently, I can say put 100 ohms here and 100 ohms here. You'll get the same power. Put 1,000 ohms, you'll get the same power. Why? Because the effective value is a function of only the current source. Okay, so let's look here for a little bit. We did some averaging, and we said the RMS value was 9.23 amps. Why isn't it half? Why isn't it 8 amps? Why is it 9? It's 9 because we averaged the square of this waveform. We averaged the square. We'll come back to that. So what that example showed, our triangle-y waveform here, it shows that if we can integrate the periodic waveform, we can compute the RMS value. And we don't have to always do the integration in closed form. We got lots of tools that'll do integrations of crazy waveforms for us. And what's really neat is the AC voltmeters and current meters in the laboratory at SDSU and at whatever school you're going to, those meters are RMS meters. What they do is they can look at the waveform, they can perform the integration, they can do the averaging, and when they give you an AC voltage or an AC current, that value is an RMS value. In the olden days, when I went to school, meters just averaged. And so if you put some icky waveform, if you put a triangle wave or something like that through them, you didn't get an RMS value. So meters are a lot smarter now. Let's think of how we can make a smart meter, just from a practical point of view. What would be a good way to make a meter that you could put in a waveform that only this waveform's mother could love it, right? I mean, this thing is ugly. But how would we make a meter that we could put something like this in and we would get this number that is the effective voltage? Well, one way to do it would be to take that voltage and put it into a resistor and then see how hot the resistor got. See that? Because that is going to give me the power in the resistor. And from that, I know the resistive value, so I should be able to get the effective DC value. And RF power meters, radio frequency power meters, frequently work that way. The low frequency meters that we use in the lab, I'm not sure if they work that way. I think they're smarter than that. But it just gives you a sense for how you could get the effective value of some icky voltage waveform. And the idea is just look at the power. You're looking at the power that's coming from the AC, but once you get the power, you know the resistor, you can get the effective DC value. Hang on to those concepts. Make sure you're good with this. But here's a waveform, and it's ugly. Before we go on, does anybody know what this waveform means, where I got it, where it might be useful? I can't think of any place where it might be useful. I just drew it because it was periodic, but it was ugly. And so let's determine the period. Okay, we got these kind of pronounced points here. We got these pronounced points here. Here is where it seems to repeat. So let's call this the period. So it's a periodic waveform, so we can define its RMS value with our integrals, and we only have to work with one period of it. Do I have to use this period? Yeah, I could start here and go to here and call that the period. I'd get the same answer. But let's set it up mathematically. We're going to use our handy-dandy formula for the effective value. In this case, it was a current. In this case down here, it's going to be a voltage. Good enough. V equals root of the mean square. So I'm going to put in my, my 1 over t, and then I'm going to just start getting areas of the squares of these. So here's f1 of t. So we're going to integrate from 0 to L1, square that rascal, and then we're going to add the integral from L2 to L3, and we're going to square that one. And can't really tell where this one starts, so let's start integrating at L3 right here. L3 all the way up to t. And we're going to square F3. So you look at this and you say, yep, even this waveform has an RMS value. And if you put this into one of our meters downstairs in the labs, you'd get that RMS value. Did I really come up with this waveform just to make it ugly? No. In my 430 lab, one of the students had hooked the transistors up well, incorrectly, and they actually made a waveform like this. It was really pretty cool. And we shoved it into the meter and got its RMS value for fun. Now, I want you to remember, and I know I've mentioned this a few times, but I'm going to pound it in like a nail. RMS, it depends on the shape and the amplitude only. Doesn't depend on the circuit, just depends on the voltage source. So what we're going to do now is we're going to take our general formula for RMS and we're going to apply it to sine waves. And for those of you that are just waiting on the edge of your seat to hear a 0.707, this is your time. So now we have a sinusoidal voltage or current. And I'm going to express the period using phase. I could do it with time, right? Look at this. I put time on this axis, but then I said we're going to talk about phase. Oops. Wish I could get into my office and get my notes and update them, but I can't. So we're going to use phase because remember, when we average this out, the horizontal units are going to cancel, aren't they? If you don't believe that, go back, look at the integral. Helps you to understand the concepts. But I'm going to use phase as my horizontal axis. And I'm going to take my sinusoidal waveform. In this case, it's a sine wave. And I'm going to apply my nice little formula for the effective value. So, root of the mean squared. Oh, just one little thing I might mention, which is somewhat related. When I draw my square roots, I always close them up because that way I know what's in the square root and what isn't. So it's just one of those dumb little things I do that really helps me keep from making math errors. When I make a square root, I say square root's done, and that way anything after here isn't my square root. But our formula for RMS, root of the mean squared, 1 over the period is 2 pi. The voltage waveform here is going to be V sine phi, or I'm sorry, Vp sine phi, because you can see Vp is the peak voltage. I'm going to square it, and here's my formula. Now let's work with it. Your trigonometric identities are just tools in your toolbox. For me, I have a beautiful table of them. They're in a book called the CRC Mathematical Tables, which is what people used back in the olden days. Now you just pull them off Wikipedia. I still use my old CRC Mathematical Tables because I know them very well, and all my books are cross-referenced. So there are places in my book where I say, use integral formula 31. But you can go to Wikipedia or a lot of different places for your trigonometric identities or your integrals for that matter. But for me, and it may be just because I'm old, I really like having them in a book that I'm very familiar with using. But so sine squared, that's an easy one. You just go to any table of trigonometric identities and it'll be there past the half angle and double angle formulas and stuff like that. And the one I'm going to use is sine squared is equal to 1/2 times 1 minus cosine 2 phi. So let's just make that replacement. And let's remember that it's inside an integral. And so what this is going to become is Vp squared times 1/2 times d phi. That's this. Minus my second term here. I'm just multiplying these out and converting it to two integrals, right? Linearity and superposition are real helpful here. We just aren't paying attention to the fact that we're using them. So I just multiplied it out. Here's my second integral. Let's see, I'm integrating a cosine and I'm integrating it over 0 to 2 pi. So for this cosine, if it was cosine phi, I would have one period from 0 to 2 pi. But it's cosine 2 phi, so that means I've got two full periods. Fine, two full periods, that integrates to 0. I don't need to do that integral because I can see it, right? Two periods, I went up a bunch of area, I went down a bunch of area, I got no area. I go up a bunch of area, I go down a bunch of area, I got no area. So I can just say that's 0 by inspection. And so VP times 1 over 2 pi, I do this integral, it's trivial, and my 2 pi's cancel out. Didn't I say that that horizontal axis here was going to cancel out? There's your cancellation right there. And I end up with VRMS is equal to VP times 1 over root 2. And of course, 1 over root 2 is equal to 0.707. So where we've gone is we started off with the idea of effective voltages and currents, and then we did a cool little integration kind of problem, which was sort of generalized. But now we've moved from the general to the specific with the sinusoidal waveform, which is so important because it's used so much. And we say that the relationship between the peak value and the RMS is 1 over root 2 or 0.707. When we describe household voltage, you know, the voltage in the outlets in your house, unless you're in Europe, if you're in the US, we call it 120 volts AC. That's an RMS value. So VRMS is equal to 1 over root 2 times V peak, or 0.707 times V peak. So if you stick your finger in that electrical socket, you're going to get 120 volts AC, but the peak will be root 2 times the RMS voltage, or 169.7 volts peak. So if we stick an oscilloscope into one of those terminals on that outlet, we're going to see a sine wave at 60 hertz with a peak value of 169.7 volts. So you remember the power in the resistor. Let's go back to our formula from the last lecture. It's 1/2 times Vmax times Imax. But Vmax is really just root 2 times VRMS. Or in other words, it's the RMS value multiplied by 1.414. And Imax is 1.414 times IRMS. So let's substitute these in for Vmax and Imax. And I get the power in the resistor is 1/2 times root 2 VRMS times root 2 IRMS. Hey, the power in the resistor is equal to just VRMS times IRMS. This is why, as engineers, we like using these so much. It's why we like using RMS so much, because I can just say that the power in a resistor is VRMS times IRMS. And do I even care? Well, you know, I'm not going to go there. Okay, so, and this holds because the power in the resistor and the 1/2 Vmax Imax and the VRMS times IRMS were all developed for sinusoidal signals. Okay, let's do another example. And in this example, we're going to do a lot of RMS kind of stuff. It's not a sine wave, so we shouldn't see any 0.707s rattling around. But we're going to do VRMS, IRMS, but I'm also going to give you some insights about capacitors blocking signals and actually changing the effective value as we go through the circuit, because I want to solidify some of the concepts from Chapter 8 and Chapter 9 with what we're doing now. So I'm given this signal, and it looks like it goes from 10 volts, and then after 2 seconds, it goes up to 20 volts, and then it repeats. So it's a periodic signal. I probably should have put a ... here, but I didn't. So I want to find the effective value of this signal, or the RMS value, and then I want to find the peak value of a sinusoidal signal that would deliver the same power to a resistor. So I take it back. We are going to see our 0.707s in the end. So what do I want? I want the effective value of the signal. That's the RMS value. I want to find the peak value of a sinusoidal signal that would put the same power into a resistor. But really the meat of this problem is, let's find the effective value, or the RMS value of the signal. So we know it's periodic, so I'm going to go back to my handy dandy formula for RMS, my root of the mean square, and I'm going to say that I can divide this into 2 integrals to make things a little easier. I'll start off with my 1 over t, which is 1 over 4, and I'll integrate the portion of it that is 10 units high, and integrate, of course, from 0 to 2. And then I will integrate the portion that is 20 units high. And hey, look at this. I never said whether this was voltage or current. Looks like it's voltage. Put a little V right here in your notes. So I broke this up into 2 segments, this segment and this segment. You'll see a lot of this as we get into Laplace transforms, where we deal with waveforms piecewise. Okay, so it's all described right here. We just have to crank these 2 integrals out. VRMS is here. Let's do this one. 10 squared is 100, and integrate the constant. We get t, and here are our limits of integration. Same deal here with the second integral. We bump through the numbers, and we get 15.811 volts RMS. 15.811. We like that? Let's take a look. Is the RMS value going to be 10 volts? You know it's not, because you already saw the answer. But this voltage, this signal, is only 10 volts for part of the time. It's 20 volts for part of the time. So is the RMS value 20 volts? Is that the effective value? No way, because it's not always 20 volts. So is the RMS value going to be 15 volts? That's halfway between them, and we are averaging things, right? No. And the reason is because what we're averaging is the square of the signal. So when we're here, our square is 100. When we're here, our square is 400. And we're averaging the square. So I look at my RMS value of 15.811, and I say, well, duh, of course it's going to be higher than this average, right? But it's going to be lower than 20. So when I get 15.811 volts for this, I go, I'll buy that. I like that. I probably didn't make an error. Okay, so for our problem, we found the effective value of the signal. It's a voltage signal. Now let's find, before we do that, let's find the value of a DC voltage that would give me the same power. That's easy. That's just 15.8 volts DC. But now I want the peak value of a sinusoidal signal that'll give me the same power to the resistor. So VRMS is 15.811 volts. V peak for a sine wave with this frequency, with this RMS value, would be the RMS value times root 2 is going to give me 22.36 volts peak. So I can put this into my resistor, or I can put a 22.33 volt peak sine wave into that resistor, and it's going to get just as hot. It's going to dissipate the exact same power. Okay, so now I just want to give you a little bit more insight. So here's our voltage, okay? Here's our RMS voltage. And this is the voltage right here, because this was our source, right? But I want to get the RMS value here. And my capacitor here is actually a very large capacitor. So at whatever frequency we're working at, 1 over j omega c, since c is so big, this thing looks like a short circuit for any AC signal because it's huge. In EE330, we use this concept quite a bit. I call them magic EE330 capacitors, which just means they're really big. They pass the AC signal unscathed, but they do not pass DC. And again, it's simple. 1 over j omega c is the impedance of the capacitor. So if that denominator is huge, the impedance is really low. But if the frequency is 0, I don't care how big the capacitor is, I got a 0 in my denominator. And so the impedance is infinite. So it's a very useful concept and quite useful when you're actually designing stuff too. But I want to find the RMS value here. So what I'm going to do is I'm going to break my voltage source up into two sources. I know that what this really is 15 plus or minus 5 volts. So I got a 15 volt DC source, and then it goes up a little bit, and then it goes down a little bit, and I got this. So I break this thing up into a 15 volt source, and then a source that goes down 5 and then up 5. And from here to the left, I can't tell the difference between this model and this model. So I know that I have this capacitor here, and it's not going to pass any DC current. So what's my waveform going to look like right here? I just want to look at the waveform. The waveform here will look like this waveform, but with no DC. So the waveform here will be plus 5, minus 5, plus 5, minus 5. Or in other words, it's going to look just like this piece of my model. So at this point right here, I'm going up 5, down 5, up 5, down 5. Let's use our formula. Root of the mean square. And I know that over here it's minus 5, here it's plus 5. So I can square that, and it means I'm always going to have 25, right? Because negative 5 squared is 25, and 5 squared is 25. So here's my integral, 0 to t of 5 squared, and I get an effective value right here of 5 volts. Does that make sense? Yeah, because it almost looks like DC if I do my square. Or in other words, I square this and I have this constant 25. And so we can see that our RMS value right here is 5 volts. But here it's 15.8 volts. important concept for you. And now, since we're talking about this stuff, let me give you another little piece of practical insight for your job interviews. Let's look at how we couple the oscilloscope, the front end of the oscilloscope. And so what we're going to show here is a probe, and then the probe, as you've seen in the lab, it has a little switch. Sorry, I take that back. For the oscilloscope, for the vertical channel, you have a selection for AC coupling versus DC coupling. And we're going to do something very simple, similar to what's going on here. If we select AC coupling, it opens this switch right here. And this is all in the oscilloscope. The probe's out here, and this is all in the oscilloscope. And so if I open that switch, or I go to AC coupling, then I have a capacitor in series with the signal that I'm trying to measure. And if the switch is closed, it shorts that capacitor out, and the DC gets right through. And of course, what's an oscilloscope do? We have a variable gain amplifier. What's that? That's your voltage per division, right? If I raise the number of volts per division, then I'm going to make my signal get a little smaller. And if I lower the voltage per division, then it's going to get bigger. And I'm going to adjust this so that my signal kind of gives me a nice display. And then the scope just displays it versus time. So the AC versus DC coupling, it just puts this resistor in. And in this case, let's say that switch is right here. If I'm in the AC coupling position and I look here, I'm going to see a waveform that goes up 5, down 5, up 5, down 5. If I close the switch, now I'm going to pass that DC part of the waveform, and I'm going to get a signal that looks like this. It's going to go from 10 to 20. So if I'm looking at the oscilloscope, if I'm in DC coupling, my waveform will be up here. If I switch over to AC coupling, it'll fall down and be symmetrical around 0. Why is that practical? Why does every single scope that's been made since my father's time have AC versus DC coupling? Well, let's say we're trying to measure a signal that looks like this. It's going from +3 to -3. I'm going to probably go for a scale of like 1 volt per division, because that way I'm going to get 3 divisions up and 3 divisions down. And this signal has no DC offset. So I can take my switch and go open, close, and this signal isn't going to move. So the answer here is we want a volt per division, and what coupling? I don't care. We're always going to get a good signal that we can see. But here's why it's got that switch. Let's say that I have a signal that has a 50 volt DC offset, or in other words, this is 50 volts of DC, and then riding on top of it, I've got about 3 millivolts of noise. And I want to really look at that noise because I want to figure out what it is. Well, if I want to see this whole waveform with my switched closed, I'm probably going to put the scope scale on about 10 volts per division, because that way this will be about 5 divisions up. But am I going to see 3 millivolts? No way. I'm on 10 volts per division. Am I going to see 3 millivolts on my scope display? I exaggerated it here. So here's what I'm going to do. I'm going to open that switch, and now my front end is not going to pass that 50 volts. And at this point right here, I'm going to see that little 3 millivolt signal symmetrical around ground, and then I'm going to crank the gain up. And now I'm going to see my noise signal. Or in other words, I'm going to put my coupling on AC coupling. So I'm blocking this 50 volts DC, and then I'm going to go to about 1 millivolt per division, and I'm going to see my noise right there in the middle of the screen. So I brought this example out just because we had looked at how that blocking capacitor changed our RMS value. But I also wanted you to see, where is a blocking capacitor used? And I couldn't think of a more practical example than the oscilloscope that hopefully you're going to use in your lab courses this week. Okay, so that's our lecture for today. Looking forward to seeing all my students in office hour. And if not, I will see you all in the next lecture.